Hey guys, in this one I'm going to quickly show an application of the envelope theorem, Lemma's lemma, and there's one thing I wanted to add in the last video that I forgot about. The envelope theorem, as we've described it, applies to unconstrained maximization problems, but you can see how it would apply to constrained ones if you just consider maximizing the Lagrangian instead of the unconstrained problem, but I just wanted to add that footnote. I don't anticipate that coming up on the exam, but I don't know, maybe it will. But you can convert these constrained problems into unconstrained problems using Lagrangian, and then apply the envelope theorem. So, proceeding forward, we're going to consider Lemma's lemma. Let the profit function as a function of the price of the output and each of the input prices be this maximization problem, where f is our concave production function. Concave is important because, as we've said before, if this thing is concave, we assume that any point where the derivative of 0 is going to be the solution, so that's why we care about that. So we're defining profit as p times f evaluated at x. Oh, sorry, should have written an x here, or a vector sign, I mean. Minus the dot product w and x. Basically, the amount of stuff we produce times the price we get for it, minus the cost of each input times the amount we used of each input. So what we want to show, oh yeah, and we're assuming all derivatives exist. First thing we're going to show is the first result of Lemma's lemma, which is the partial derivative of profit with respect to the price is going to be equal to this y star of p and w. How can we show that? Well, let's apply the envelope theorem. This is the solution to the maximization problem, so the envelope theorem tells us the partial derivative of pi with respect to any of the parameters is going to be the partial derivative of the objective function with respect to that same parameter evaluated at the optimum, and plugging in the parameters we have. But this here is the objective function, and the derivative of that with respect to p, there's no p over here, the only p is here, and the derivative is just going to be f of x. And now we just plug in whatever our x star is, and we get f of x star, which we can write as a function of p and w. And look at that. That's exactly what we've defined y star as. So I can get rid of this part and replace it up here with y star. And that's the first part of Lemma's lemma. The envelope theorem makes this problem much simpler. Essentially, you just take this, differentiate with respect to the parameter, and then plug in your optimum x. The next thing we're going to show is that the gradient, or I guess, sorry, we'll say the optimal x, the vector of optimal x's, is going to be equal to -1 times the gradient, the w gradient of profit with respect to p and w. So, first thing we're going to see is we're going to take this. We're going to take the w gradient of profit because we can use the envelope theorem. So, the w gradient, or sorry, if I've been saying profit, I meant prices. My apologies. Or wait, no, sorry, this is profit. It's been a long day, I'm sorry. So we're going to show that this gradient is equal to negative times the x star vector. So how do we do that? We can apply the envelope theorem. W is our parameter, and so each of these partial derivatives in the gradient is going to be equal to this partial derivative with respect to w evaluated at the optimum. But this is going to be equal to negative w1x1 plus w2x2, and so on. So each w is going to be right next to an x, and that's the only place it enters. So we know this gradient is going to be equal to negative w1, or sorry, negative x1 at the optimum, because we take the derivative of this with respect to wi, and then evaluate at the optimum. So we're just going to get negative x1 star, negative x2 star, and so on. And I could write all of these as functions of p and w, but I left it off for space. So finally, this is just negative the optimal x vector. And so we multiply both sides by -1 to get x star vector equal to negative the W gradient of profit. And those two things together give us our Tillings lemma.